Hello, everybody. Thank you for inviting me to this very interesting conference. I've been coming in and out of it for some years. Some of you know me from before, and very briefly about my background. I've been doing databases since before non-SQL databases. I mean, before SQL. And then I did data warehouse since 95-ish, something like that, doing Kimball style data warehousing for many years. And some of you who are old enough will remember that on the data warehouse toolkit book, there was a CD with some example documents. In those documents, there were little concepts outlining the structure of the dimensions. That was sort of what inspired me to go graph, really. Because 10 years later, I picked up concept mapping for dimensional design and did knowledge elicitation using concept maps in interactive brainstorming kind. And there's not a long way from concept maps to graphs. So about 5-6 years ago, I said, well, now Thomas, you go graph, right? So there will be a lot of graph in this, and the title of this presentation is Graph Normal Form, right? For many years, I've been thinking that there ought to be, or there is probably sort of a common denominator of all data models. And I've been thinking of it as the Creole of the data models. Creole is, a name for, made up to the occasion communication tools between people who don't speak the same languages. And here are some of the well-known pidgins and Creoles. And I think that I have now found the data model Creole, and that's what I'm going to talk about today. So I started out, like everybody else these days, to ask GPT. Are there really many different languages in the data model business? So I asked, tell me about 25 most important data model types. And the first answer I got didn't have a fact model, and I think fact models are a very important kind of data models. So I pointed that out to GPT-4. And here comes the reply. I apologize for the omission. The fact model is indeed an important data modeling technique used to model complexities and so on. So there we have 25, 6 maybe, modeling languages, including fact models and graph data models, and RDF data models, and OWL data models, and UML data models, and so on. So then I said, well, what about data vault and anchor models? Are they also not important data model types? And GPT-4 had to admit, yes, both data vault and anchor models are important types of data models that have gained popularity in recent years. So that sort of taught me that, yeah, okay, GPT-4, fine, thank you very much. I needed this information. So what is it that has been going on with data models? If we look at it from a historical perspective, you have Chen's entity relationship modeling style to the left, which I actually like a lot. I come from the IDMS world, and we actually use Chen as the data modeling paradigm for building codicill databases. And at about the same time, we had these tabular structures in the relational model from Dr. Cott and Chris Date some years later. And that evolved quickly into the right-hand side with the entity relationship diagrams with crow feeds and stuff. So that's sort of what happened by selection, I would say, because Chen chose something that to me looks pretty much like, but other people decided to choose tabular representations, and the integer relationship models included some kinds of arrows. But in the relational model and the SQL implementation, relations are second-class citizens. You don't have to actually do them, and you can actually ask the query optimizer to pretend that there is a physical relationship when there is not. A lot of what has been going on here is sort of the quest for the inner structure, as Chomsky would. The inner structure has another name. Finding the inner structure is called normalization, right? And it's about identifying functional dependencies between keys and attributes of relevance, as Chris Date would say. But the same picture of those three tabular constructs can be drawn as a little concept map. That's drawn to the left. And to me, that's sort of showing the inner structure of the semantics of those three tables. So that's sort of the schema that I saw, and I delved into this discussion about functional dependencies and what's not functional dependencies. And actually, it's a weak point, if you ask me, in SQL. If you go to the SQL Foundation, you'll see that functional dependencies are a very complex matter involving around 36, I think, complex rules that the query optimizer must perform. Right? So it's about these things here, right? Identity. I don't know if you remember the little poster that was issued together with the Database Programming and Design magazine in the 80s. It has a little database of puppies and kennels and tricks that the puppies could in order to be sold. And it's here depicted as a concept map. But what is obvious when you look at it in this way is that, the identity of a puppy trick must be something that is sort of identifying it both from a trick and a puppy point of view. And the same thing for the uniqueness. Obviously, the uniqueness of a puppy trick must be sort of inherited from the trick and the puppy. So dependencies are much easier when they are explicitized as they are in these kinds of diagrams, right? So the tabular way of doing things is, one of the paths that our evolution of data models has taken. The other path, I think, is here. Going back to the 80s, really to Dr. Nason in Brussels, we got the relational model, ORM, which evolved into fact modeling today. It looks like a graph to me. It is a graph, right? And the other data modeling practices evolved, which also look like graphs, not least data vaults or anchor modeling. So if you ask me, everything looks like a graph today, but the underlying technology is not necessarily graph, and that seems to be the problem. A lot of the discussion yesterday about automation and stuff, I think, really sort of underlined that there are limits to how far you can take to build a good semantic network. And that's what this is all about. Here is a little property graph example. It's actually the employee department model. So the idea in property graphs is, in a way, similar, you might say, to a third normal form representation in the relational model. But we have it in a simpler structure, and we have explicit relationships. That's sort of the whole idea of a property graph. Another standard is RDF. RDF has been around since 1999, and it's also a graph. I'll come back to the property graph standard in a little while. RDF is consisting of actually what is in their own language called triples. Triples is the core of the construct of subject, predicate, objects, which also means that you can actually read graphs like a collection of little sentences. Woody Allen is an actor, right? Property graphs look quite similar, and actually structurally there's not a whole lot of difference. And you can also read property graphs as subject, predicate, objects. But talking about the semantic standards, RDF and so forth, in these days people are doing a lot of effort to implement knowledge graphs. And if you talk about knowledge graphs, you are sort of forced to recognize that there are knowledge representations out there implemented as RDF. Here are some good examples. They come from a book by Andrew Iliadis, called Semantic Media. Like Wikidata, Google Knowledge Graph Search APIs, Microsoft Search APIs, Financial Industry Businessology, and so forth, which are more or less all of them represented as RDF, meaning that you would like to include some external, metadata in your own knowledge graph, knowledge about the world, because you do also source data from outside of your own organization. So the RDF and the property graph have to coexist. Let me briefly go back to the beginning where I skipped one slide, this one. RDF has been a standard since 1999. Property graph is in a way already a standard because Apache has had a property graph language called Gremlin since I believe 1909, something like that. No, sorry, 2009. So it's around 15 years old. Gremlin is reasonably popular also in larger context. But the dominating picture in the property graph world is the property graph as sort of expressed in products like Neo4j. That has now become an international standard, and you should be aware of this. There's now something called the SQL property graph query. It is by now an international standard that you can actually order from your local ISO member organization. And just go and buy it on their web shop. Now, SQL PGQ is an add-on to SQL. It's sort of a layer, a read-only layer that you put on top of SQL, and it enables you to do property graph queries on top of SQL tables. The full property graph implementation is described by the GQL standard, which is a standalone declarative property graph. So it's much like, think of it as a SQL for graphs. It shares a lot of the syntax for graph queries with SQL PGQ, but it is completely standalone. The schema facilities in version 1 are very limited, but it's there. It is now in the status called Draft International Standard. The ballot, which is sort of the collecting comments from all member countries of ISO, started yesterday. And that means that you can actually go to your local ISO member organization and ask to get a copy of the GQual standard ballot proposal. And then you can submit comments to the committee if you wish to do that. Down at the bottom here, there's a link to a PDF of a presentation that the convener did back in October that will give you a brief introduction to GQual and PTQ. But it is out there now, so these things are really, on the street. So to summarize graphs, for those of you who are not familiar, graphs are really the study of graphs, which are, modeling pairwise relations between objects. Look to the left, it's simple, right? It becomes semantic because it's the subject predicate object constant, meaning that there are semantics in the relationships. Relations share subject predicate object. And, this is not something that's just in graph database. The ISO Common Logic Standard has it as well, and it's sort of used to build conceptual graphs since, I think, fact modeling triples in RDF and semantics and ontologies. Relationships, or edges as they are also called in property graphs, functional dependencies in relational theory. All of this is sort of the semantic pattern subject predicate object. Now, a natural question when you deal with this, can we normalize graphs? How do normalization relate to graphs? And actually, turns out that there is something called graph normal form. Graph theory is based on series mathematics. It goes back almost 200 years, really. And there's been a lot of mathematicians doing graph theoretical work. And one of the findings is graph normal form, which is at least 25 years old. So what the mathematicians were looking for was ways to build a canonical representation of graphs in order to be able to compare. That's a difficult question. Having two graphs, are they really the same graph or what? And they found logic to do that, and they called the result graph normal form. And it goes back a long time, but the actual really force player on this scene now is a company called Relational AI. And I really encourage you to look it up, because what graph normal form essentially is, it's decompositions of relational normalization going to the sixth normal form. Now, doing that, you see that one of the problems in relational modeling is that properties come home, so to speak. You again identify the dependencies between business objects and their identities, and the properties that depend on the identity of the object that they belong to, so to speak. So they come home. Now that means that this is actually, the most atomic decomposition that we can get of any data model. Here is a little graph, and I'm sorry, graph normal form is one of those cheap things that Mark mentioned. They are directed acyclic graphs, and that's what they are. They are really the atomic level of relationships between and their semantics. If you look to the right here, this is actually a plant UML input file that produced this diagram, and even the plant UML syntax mirrors the subject object predicate pattern. So if we imagine that we build an environment where we have this as sort of the core of the schema information graph, then we can do things. Here's a very good explanation of a graph normal form delivered by Mulham Arif from Relational AI to the Linked Data Benchmark Council in June of last year. It's really very good. So having a canonical graph representation of your metadata components enables you to do projections or materializations into many different formats. Here is a property graph derived from this canonical form, but looking suspiciously like a third normal form SQL construct, right? So it's straightforward to do these projections, and actually you end up, if you have this kind of vehicle for generating physical data models as graphs, you get another complex metagraph, right? That sort of traces all the components of actual implemented instances of graph back to this canonical model. And this could just as well be SQL or other property graph representations, or actually any data model that you like. So what can we do with that? Well, the canonical graph normal form model is home for much of metadata if we have it. For instance, mapping to SQL PTQ from GQL could be solved using the canonical model. Lineage, provenance, you need a canonical model for that because you have a really complex graph. Things are being reused in different contexts and so on. Functional dependencies can be more specific, meaning that the need for inferencing in query planning goes down. Versioning can be handled on that level, generating physical instructions to the query optimizer to actually do the complex timeline logic for you. Can enable consistency between different data models, breeds, and you can even extend it to do ledger management of immutable chains of blocks controlled by the canonical data model. So what you need to realize is that the metadata and content evolve together, and one of the big advantages of project graphs, at least, is that you have typically a schema-less development environment. You load data without writing schemas. You inspect data using graph queries. You do iterative changes to your graph model, sort of working your way towards what you want at the end. And the canonical form can remain the same even if you do structural changes, such as rearranging the allocations of properties to nodes and the relationships and so on.
1 minute left.
Yeah. So this is in contrast to a relational model where canonical form is not easy to visualize. Using this, you can build little graphs, data controls, I call them. It's metagraphs we're talking about, that actually control both the canonical model and the implementation models. Can look like this. Here we have a canonical model. Here you have a timeline metadata entity, another timeline metadata entity, and an identity metadata entity related to the canonical model. And when you derive physical models from the canonical models, these things that describe these aspects, timelines, identity, and so on, can be inherited down into the physical models. So that is what I am working on these days. The SQL the SQL standard version 2 is a bit immature on the schema side, so I hope to really enhance the schema in version 2 of GQL to include capabilities like this, because as much as you guys want, I also want to do temporality and immutability and stuff like that. Right, but I think SQL has too many limits for it. I think graph is the solution. You are most welcome to join the bandwagon.